Hi everyone, today I'll talk about our work, accelerated sampling of rare events using a neural network bias potential. I'm Xinru. This is a joint work with Rasul, Jose, and Wei. And this has been accepted at the NeurIPS AI for Material workshop and chosen as a spotlight presentation. So first, let me talk about the motivation of our project. In material science and biochemistry, we want to sample rare events that are associated with specific physical phenomena and estimate the probabilities. This is crucial to help us to understand some properties of the materials and the proteins. In this work, we focus on sampling the rare event that one molecule transits between two stationary metastable states on a 2D plane. And the dynamics of the molecule is described by the overdamped Langevin dynamics. Here's the discretized Langevin dynamics equation. We can see at each step the movements of the molecule has two components. The first part is the gradient of the energy function. And the second part is a Brownian motion, and the size of the Brownian motion is affected by these variables. The most important one is the temperature, the capital T here. And the specific problem of our work is described as the energy function is this function, and the plot is shown at the right-hand side. One important thing is there are two local minimum, A and B. And A and B are also the two stationary metastable states. Once the molecule falls in A or B, it will be very challenging for it to escape. This energy field is also a double well potential field. In the center, we can see around 0, there is a big energy barrier, which blocks the molecule from moving A to B. And the rare event we're interested in is the molecule starts from A and eventually moves to B. In our simulation, we present the trajectories as nu, which is from x0 to xn. It's the position of the molecule at each time step. And n is the deadline that we give to the molecule. So we are interested in the rare event that the molecule moves from A to B before a time deadline. And our bias potential is parameterized by a neural network theta. Theta represents the parameters of the neural network. So we formulate the probability, the estimation of the probability as an optimization problem. And our objectives are, first, as we solve the neural network, we want to, after biasing the dynamics, we want to ensure all the trajectories reach B. And for all the successful trajectories, the distribution of the biased ones and the unbiased ones will look very similar. So after biasing, we want the distribution of the successful trajectories to be similar to be before it is to be the unbiased ones. And we write the optimization problem as this equation. We want to solve theta, which is the neural network, to minimize this whole thing. The Q is the distribution of the biased trajectories. It is also how we sample the trajectories. And first, we want to minimize the F smooth, which represents the first objective. This will ensure all the trajectories reach B. And the second component, which is this log dq/dp, corresponds to the second objective. This EQ log dq/dp, which is the KL divergence between distribution Q and distribution P, will make sure that the two distributions look similar. And the pipeline of our method looks like this. Given the Langevin dynamics with energy U, we will want to solve the bias potential UB theta. And using the UB theta, we will bias the dynamics and to sample trajectories nu. With other trajectories, we will use the optimization problem in the last slide as our loss function to train the neural network. And this middle part is our training loop. After the training, we will use importance sampling to compute the probability of the rare event. This shows the training process. The bias potential is initialized randomly. And after training, it will eventually make a large proportion of the trajectories to move from A to B. And we can see the bias potential evolving first. So in the end, it will converge to this plot. During the training process, the trajectories will start to move from A to B more and more. So there are two channels of the rare events that mostly happen is the up and down. This because the molecule want to try to avoid the center energy barrier. So they will either move up or move down to move to B. And on the left-hand side, there's a large portion, some trajectories that are not successful. So they are moving randomly close to A, but never escape the energy well. And here is the comparison between our method solved bias potential at 1200 Kelvin and then the ground truth bias potential at 1200 Kelvin. We can see the shape looks very similar. And how do we get the ground truth? We solve the PDE that corresponds to the SD process. And on 2D, this is possible to use finite element to solve the PDE, but in higher dimension, it becomes very infeasible. That's why we need our method to solve the bias potential and to help us to sample the rare events. And our project goal is, the main goal is to sample rare events effectively. It's not to solve the bias potential, but still they look very similar, although our method does not involve solving the PDE. And there's another functionality of our method is to combine all the past knowledge into one bias potential. So in higher dimension, or in the case there are multiple channels, it's very possible that in one training loop, we only capture one channel of the rare event transition. For example, on the first plot, we only have the molecule moving in the up channel. So they always go up to move to B. And in the second plot, we have the molecule always move down to move to B. In this case, we want to combine them into one bias potential. So our method has another optimization problem that corresponds to this setting. And in the end, the combined model will look like this. The bias potential still looks similar to the ground truth one, and it's able to sample trajectories in both channels. Here is the training process. We can see first the trajectories that are sampled are moving from left to A, from A to B, and then they go in both channels equally. The second part is how the bias potential evolves. It will move from a randomly initialized bias potential to a potential function that will move the molecule from A to B effectively. And here's the comparison results between the trajectories. The left-hand side is the trajectory sample by our method, and the right-hand side is the Monte Carlo sample trajectories. And one important contribution of our works is we provide statistical guarantee to our estimator. We use efficient sample size and the coefficient of variation to measure the robustness of our method. So here's the results for temperature 1200 K. We show the results of both settings of our method, A and B, and also Monte Carlo. So we can see the confidence interval for method A, it's very similar to the Monte Carlo's confidence interval, and the variance is smaller than the Monte Carlo ones. And the coefficient of variation is also much smaller. The success rate is the how many success trajectories there are in the sampling path. In the sampling in the test part, we can see the success rate is much higher than the Monte Carlo. This means our bias potential successfully moves the molecule from A, helped move the molecule from A to B. And if we combine the training and test time, the method A is 4 times faster than the Monte Carlo. Also, one thing to note is the training time is a one-time cost. It will not grow as we want to sample more paths. Only the test time will grow. And the test time is about 40 times offers 40 times speed up compared to the Monte Carlo. And we also offer the robustness for the estimator. We want to measure how the standard deviation of the estimator decreases as the number of samples grows. The first plot shows it decreases as big O of 1 over square root of n. We plot the STD of our estimator versus the number of samples. We can see that, for example, the red line, it will decrease. The red line is the big O of 1 over square root of n, and the orange line is our method, the STD. It decreases faster than 1 over square root of n. And similar results are also shown for 1000 Kelvin. And the ESS and the test time will grow linearly as the number of samples grows. Thank you for listening, and feel free to ask any questions or send comments to me. Thank you.